Welcome back to Cloud Computing and Big Data, our lecture 12, the second part. And lecture 12 is about Docker and container management at large. So the first part really was introducing us to the idea of using containers, containerized applications, which are really often used in cloud environments for many different purposes and applications. We have also discussed a little bit the difference between virtualization and Docker and containers as such. Also made an analogy with ships, basically, that you already know have often, large ship with many containers on it. And the analogy is really that the container is nicely having everything included what you need for an application. Let's say different libraries, different data sets, and with this, it's a very, let's say, fine way of also porting containers between different cloud vendors. And this is the topic that I also will pick up again, also now in the second part, where we have much more variety like in the first part. So we will talk about some other cloud environments from EVM, for example, but also have the examples quite intensively about a very specific niche, which is the engineering niche in terms of computational fluid dynamics, where we look in how, for instance, the Uber cloud is basically dealing with this complexity for customers in the cloud and make it simple. And I should also mention that Uber Cloud is now SIM-R, basically a new, let's say, venture, but of course goes back to the tradition of Uber Cloud. So the slides you will see are essentially provided by me, by the CEO that I know basically personally, Wolfgang Gensch. But of course, the approach of SIM-R is continued to be serving engineering disciplines. So we will look at this, we will see how containers can help in that context, and then we'll elaborate a little bit also how the container management and orchestration works, maybe with other tool sets like we were alluding to Apache Mesos, for instance, or thinking about the bigger story with Kubernetes. So let's start section 2 again with quite, let's say, impactful slide I found from Google Cloud. So this is essentially an overview where all the different, let's say, areas are for industries, right? So where, containers have an impact in all of these different industry solutions. And as you can imagine, with some of the areas, for instance, manufacturing, healthcare, and life sciences, the experts that are working in these fields, maybe not really necessarily computing experts, right? So hence, the idea of containers is also making it easy for, let's say, application-specific developers to really, or basically people that use just applications that, make it easy to ship that already prepared inside a container and, then use it. And the underlying example that you here have, for instance, also as the IKEA example here that some of you already know, probably from the app, you can basically point, you have an image analysis that directly points to the product, where it is in IKEA and so on, when you see it obviously on the floor there. So hence these technology has been by now really matured and is integrated in almost all cloud environments. An interesting thing is that you here see is also the nice cooperation between the tools you already know, that Jupyter can be part of a container. The deep learning packages and deep learning tools we know could be part of a container, and then the Kubernetes that is managing all of these cluster areas, all part of the Google Cloud with different emphasis, of course, but then enabling us really to also, let's say, orchestrate different containers together, let them work together. You have seen the microservices, which is then one way of the extreme, if you want, which really having smaller services, but really combining them then to the greater application. So in a sense, you see that there's a big market impact. We looked a little bit also on the idea where now containerized applications are in the Google Cloud as one key example. Again, the message is MS Azure and also AWS have, of course, other examples too. And here, if we go in the category of containers, for example, you see what we already discussed in the first part, container registries, where you really have, let's say, the Docker images stored that you then, of course, can also download and instantiate, right? That is now the point when you would bring that in an idea like here, for instance, you would have essentially Kubernetes managing this so that you start the application inside the container when the container then is in a one respect deployed in the infrastructure, right? For this, you need the container runtime running where the containers are living inside. You see also good examples of again, deep learning containers, right? So this is something which we know from lecture 7 was quite cumbersome. You see already the example that we had in lecture 9, where we had also, the Google Cloud Platform as a, let's say, interesting cloud really supporting the development. So you see here Cloud Build, solution for running build steps in a Docker container. So in a way, you have here also then, again, Cloud Code. IDE supports to write, run, and debug as a Kubernetes application. So these are all things where Cloud Run environment for running containerized apps. So you see that the containers are really part really of this process that we discussed on a, let's say, more higher level in lecture 9, and can be then, of course, then combined with, let's say, tools we have learned in lecture 7 and 6 with deep learning, for example. Also, the other term that you also see is quite prominent, usually in the cloud, is Kubernetes. The kubelets we discussed a little bit also. Just want to make the case again that essentially this is something which is also, let's say, everywhere in the cloud these days. Now, the benefit that you have by this in this containers is, again, think about what we had already earlier, that there's so many different versions of deep learning packages. There may be different underlying libraries that you need for different hardware. So having this all conveniently in the deep learning container is basically quite nice. So when we now look at this idea as an example, because we had this already, if you want, a little bit in our practical lecture 7.1 and lecture 7 and so on, we looked at the AMIs, if you remember, from AWS. So it's very similar, like the idea there. We had in this AMI images really, which are, let's say, purely virtualization. There, the idea of having all the different packages together with an operating system, if you remember. Now, what the difference now is here is that the deep learning containers have, let's say, the same consistent environment that you have. But of course, remember, we have less storage footprint because here we don't really have the operating system alongside. So in this sense, this enables us much more portability, right? So this is now a very beautiful concept when you think about that you have everything in the container that you need to do for, let's say, your idea in a Docker container doing deep learning. You have, let's say, the right set of packages, but also your own code running there quite nicely, a Python code using, for instance, image analysis. Potentially have also parts of the, let's say, images or the data that you have already, in the container as well, or some tutorials, depends what you really want to do with it. But the cool thing is then really from this that you can ship it to other clouds. Like, again, our analogy here with the different boats, right, where you can put the containers in and then, have another container ship, perhaps also then illustrating that you can maybe put the container from the Google Cloud then back to Amazon. So hence, it enables us really an enormous, let's say, way of using different solutions in different cloud providers, because as we said, also the Docker technology is there quite prominent, and often it is also even combined with Kubernetes. So these are things you already know from a little bit lecture 7, but now we really have the containers as a bit more specialized idea how to really do this in the cloud. And you can go on, and you see that PyTorch was another example, for instance, of a deep learning package. And here's another example also of a cloud with the Alibaba cloud in China, which of course has also products around high performance clouds that you need for machine learning and deep learning, right? You see also quite prominent ones like machine translation. You would say that's sort of a NLP downstream task. That's an example. Image search, speech interaction, and so on and so on. Here you see also then, just as an illustration here, that the deep learning framework is then, of course, also based in this Alibaba cloud on a container technology. that you basically have here with NVIDIA's container for PyTorch, meaning that underneath you would have also then the GPUs that you need, supported by this container. So you have the right drivers and so on that you need to really leverage, CUDA from NVIDIA. And you see also again that of course you can, go then to all the different cloud vendors here that we see the hyperscalers if you want, and they have very similar solutions. So this is something which just should illustrate you that there are different clouds now, not only just the hyperscalers that we have seen already. And here is also a nice connection again to a lecture you already heard. This was a lecture given by Shadi, if you remember, recently. But here you see the association rule mining algorithms, a priori and karma, for instance. So a priori, we have also talked about FP growth, but karma is yet another one that is also in this arena. And the way how it works then in this EVM Cloud Pack is again that you use virtualization, and of course then with this also the container technology and Kubernetes, right? So this is then also integrated, for instance, in the EVM Cloud that we basically see here a little bit on a high level shown. And what I also wanted to make the point with this is that always think about that maybe some of the aspects some of the applications you're going to run in the public cloud, but also maybe some of the aspects, in your data analysis or your image analysis, whatever it is, if you have sensitive data to analyze, you maybe want to do this in a private cloud. Hence, the container technology enables you to do this as well. Having the same functionality as a container may be put to a public cloud for several data sets, and for others, you keep it in the private cloud. Hence, this multi-cloud is really, which here is explained a little bit, an important factor of thinking about this portability again, but also using then, let's say, the implementation, the applications, the libraries with maybe different data sets in different clouds. And this was yet another example. And I also have already introduced you a little bit to this UberCloud and SIM-Air containers. So here we think about that this is a very niche market, if you want, for engineering. And I think it's a quite nice success model because SIM-Air really for basically the SIM-Ops, what they here explain also in the press release, is of course now a nice level up. If you want, they have secured quite some investor money. So you can see that these ideas from UberCloud and using containers that you see a little bit illustrated here with Kubernetes and Docker for all these different engineering packages. And we will look into some of these problems now so that you understand a little bit what we mean with engineering, especially if you talk about the fluid dynamics and fluid flow and so on. So with this, the cloud is ideally, let's say, in the niche market of providing solutions inside the Docker containers for all of these different, let's say, engineering packages and libraries, while still being portable to different cloud vendors, right? HP, Google Cloud, and so on and so on. So hence, in the overview that we have now, we will dive a little bit more into several applications. You see, for instance, ANSYS is one of those packages that is really for computational simulation essential. It has lots of solvers that you basically need to understand, scientific or engineering simulations, also often used actually in HPC environments. So let's look a little bit what these are used for, right? And I just wanted to make the case here a little bit that I would like to thank, of course, here Wolfgang also for providing the slides. And then also thinking about, how this community in a way is very interconnected. You see here, for instance, one of the, let's say, publications we had, right? So it's a sort of personal point that you see that 10 years ago, more than 10 years ago, we published together. So, Wolfgang Gensch in grid computing. And this was basically something where then cloud computing was not really fully established. It came over the years more stable, that cloud computing was seen as an evolution really from grid computing. And this is something where you see here still now basically Wolfgang has then took the UberCloud here and has then created a company. And still this is an interesting point that, you know, when you go to the conferences, you meet the people, you have a community in cloud computing that seems to be massive, but still, you know, basically it's large, of course, but many players remain the same. You know, take me, for instance, I'm 20 years now, more than 20 years in HPC, cloud computing and AI. So of course, with this, we basically meet people in along these times. And I'm saying this because this is an interesting factor, hopefully also for you as a community, having these, let's say, connections and having these opportunities really has also driven lots of research projects, of course, in the past that you see here. DASA, for instance, was a project bringing all the European HPC systems together, which are now at that point in time were transitioned to PAAS, the Partnership for Advanced Computing in Europe, and even now led to the Euro HPC joint undertaking over many, many years, really. And now we talk with DASA really about a decade, right? So they took now to establish the Euro HPC JU that I already introduced to you, where in the moment HPC is provided essentially to scientific engineering communities. Hence, let's go a little bit more now back to the UberCloud and SimAir. It's also interesting for us, basically, that our academics to see what industry is doing, especially if you know the persons involved. Also over 10 years, you can observe them or what they do here in industry and collaborate with them, of course, where we can. So here's a couple of, let's say, high-level areas where UberCloud and SimAir having applications. Here on the left hand is about the UberCloud area. You see even COVID-19 was part of it. And here's the combustion, automotive, and turbo machinery, where we will talk a little bit more about it, because this will include partly already fluid flow and so on, and computational fluid dynamics techniques and so on. So on the right-hand side, you see also the case studies here from the SimAir I added, where again, aerodynamic CFD simulations in the Advania HPC Flow Cloud, right? So here, this is a mouthful. So this means really a lot of information. Firstly, aerodynamics, right? So we see a car, aerodynamics. This needs usually for design and develop of this car CFD simulations. You don't know what CFD is. We will see how that materializes in the next couple of slides. So we have computational fluid dynamic simulation that can actually then, you know, simulate this aerodynamics effects. Then we also said with this, the Advania HPC Flow Cloud. So hence Advania should ring a bell to many of you, right? I already was introducing this a bit earlier. This is, of course, here in Iceland, the idea to compute basically more green. So, and you see other CFD examples also there. For instance, the wind turbines is a traditional area where also CFD simulations, of course, with wind flow, is there wind turbine aerodynamics. And you see many of these kind of engineering problems. Also, artificial intelligence is something which is now coming more to, let's say, manufacturing areas and so on, where, of course, then the containers that we basically set around deep learning could be also useful here. Now, again, thinking about how old this company is, and as I said, also now, of course, you know that it is SimR by now, or it's called SimR, but you see also that from the beginning, the idea of using container technology was basically part of it, right? You see 2013 HPC container development, and it's basically still, let's say, in many of the HPC centers, a topic which is very new. We use Aptainer or Singularity. I will come to this at the end very briefly. But I think what to just show you that during the course of the development of this company, it has done strategic partnerships with larger cloud providers. So in a way, you can see they don't see UberCloud and SimAir really as competitors, but rather as enablers of more engineering, let's say, users, right? Because you can, of course, choose then to use one of these bigger ones for doing the actual computing, while you use, of course, the containers provided by UberCloud or SimR. Then you see some strategic partnerships with ANSYS, for instance. So it's also important. ANSYS, if you remember, was one of these important libraries and packages. And you see here computer-aided engineering software containers and so on and so on. So the company heart, if you want, is really containers and maybe a bit of Kubernetes. And around it, of course, many things have been done, I think quite interestingly, really, to enable these partnerships to, in a way, position this company in a niche market in engineering, which is now, of course, very successful. You have seen with SimR going the next step. Now also thinking about the relevance when we also talk about HPC, right? So I talked to you, we have the other course, high performance computing. This is really low level. And many of the different, let's say, packages, so ANSYS, for instance, or you can go also to OpenFOAM, for instance, they are all, you know, really leveraging high performance computing. So when we talk about cloud HPC platform, that means usually there is somewhere HPC really with good interconnects somewhere in the cloud, but usually it's quite good hidden, right? So you see here a good example that the engineers are rather using, you know, iPads, using quite nice graphical user interfaces in the engineering discipline or computer-aided engineering tools. You see here ANSYS cluster demo. So basically, I've always agreed you don't have a job script, something very low level that you usually do in HPC. Hence, the idea of using this as a cloud abstracts really a lot from the technical complexity. And by using these containers, you can really provision this to the users at scale while hiding this complexity. And that's why I think the cloud HPC platform approach is very attractive also in the engineering approach, because many of the engineers, they want to focus on the aerodynamics of a car, on the, you know, aerodynamics of wind wheels, wind farms, and so on and so on. So hence, something which is really a helper tool here, where again, of course, the Docker and the Kubernetes come in underneath, which of course you don't see really when you interact with this engineering applications. It is under the hood, and of course, a very powerful element. Now, I talked often about CFD, and it's of course clear that the HPC course will talk about much more in details about this. So I have it just briefly mentioned here so that you understand this term as one of the examples in engineering that really can use cloud HPC a lot. So you see here the race car, for instance, how that materializes when you simulate it. You understand by using many different nodes for complex simulations. Then the fluid motion, and this is also includes, of course, gases, air, liquids, and so on. And you would do this with so-called numerical methods, right? So this is different ideas how you basically you know, or different, let's say, approaches really how you deal with this phenomena of fluid flow. Hence, it's a huge topic, and you can also see that has some overlap from, let's say, simulation space to experimental fluid dynamics, where you really have experiments maybe in a chamber, or we have theoretical fluid dynamics, lots of, let's say, theoretical assumptions and formulas that we see also very soon on the next slide with Navier-Stokes, Lattice-Boltzmann, and somehow the simulation is in the middle, right? So fluid dynamics and fluid mechanics to simulate this phenomena will basically be to validate a little bit the data that you have in the experimental fluid dynamics and leveraging some of the theoretical fluid dynamics. And there are certain established ways how to do it. Now, if you want to simulate, let's say, waves here or so, that are shown there, the real fluid flow, basically. There are different approaches to this. One is essentially around the Navier-Stokes equations, saying a PDE. This is a partial differential equations used in numerical computing. So here we usually would dive a little bit more deeper, right? So, and of course, something where the other course again will be also going much more into depth, especially the last 2 years we were teaching the HPC course with an emphasis really on CFD by also one of my PhD students, Reza. Now the alternative would be Lattice-Boltzmann equations that have another way how to deal with it. And the interesting thing is that you can really then simulate this fluid dynamics in basically discrete points in space and time in a way. So that is the wording there. So this is a usually very iterative approach, right? So you have numerical approximation step by step, and then you over time can simulate, let's say, this wave height and how it then propagates over the ocean, for instance. Hence, an interesting field of understanding this fluid flow. And of course, with this, you directly come to numerous applications in the engineering domain, right? So you see here crash tests of cars, or again, how it is basically with the airflow around the car to basically save fuel and so on. So these are all, let's say, solutions that you have really fluid velocity. You have basically, of course, a stress on materials also taken into account when you have a crash here. Here below, you see the fire, for instance, that is starting, and then the kind of, let's say, the smoke really coming over and creating alongside these meshes here, the expansion over time, right? So this is, again, showing you nicely that these simulations, of course, have this interesting over time simulation factor. And there are really many approaches that, let's say, enable this then computation-wise, also that you are able to use, let's say, more than one core for this or one node. So can really use MPI again. We talked about this briefly, message passing interface already. So really interact with many different nodes. And with this, you have this idea of also simulating finite elements, or is it finite elements methods really, where you see a certain mesh that you then have basically here also even refined in the smoke example. You see that here every now and then we basically increase a mesh or make it lower depending on the computational complexity. So this is a technique, for instance, called adaptive mesh refinement, and also something we talk much more in the HPC course about. A topic which is really rich, and there are lots of application examples and libraries existing. When you come to the different codes then that enable this, you are basically somewhere in the space of ANSYS, for instance. There are very different specific packages that you see here. Even MATLAB is here and there used. So that is something that you maybe know from other courses or so. And they all have a different unique selling proposition and are also here and there supported, of course, in the different cloud vendors, also, of course, with UberCloud and ZimAir. So by doing this, of course, again, the idea comes into play. Why not using a Docker container, right? And you see here as an example, bridging now what we discussed about the fluid flow and the packages and what we have to provide then in the Docker container would be now the open source package OpenFOAM, right? So this is a known, let's say, is a known solver really, following the numerical approach we just discussed, that has really lots of utilities you need as post processing really for CFD problems and do the, let's say, simulations. You see here a large eddy simulation LAS mode with OpenFOAM, for instance, of understanding what's happening with a chimney somewhere in an industry, just as an example. And OpenFOAM is free, so basically that's something you can just install freely. It is object-oriented, and already inherent is a parallelization approach, right? So this means domain decomposition is in distributed memory with MPI. We discussed this in earlier lectures. So this is something where really the code is already done for scaling up, right? And then you have, of course, several examples. Here's the stack exhaust that I just mentioned, but this can be all put into one container. And then with Kubernetes, you scale it across the whole cluster, right? And roll out these different containers depending on your needs and the complexity then also, of course, about the about the domain you want to do. So this is something which, of course, then needs more computing in the lower level, which you have seen here again. So then, of course, all my points that I had in earlier lectures when we were using, for instance, Microsoft Azure, you remember still, hopefully HD Insight and so on, of course, now we're talking about that there's then, of course, costs involved, right, of using the lower level infrastructures. Hence, there's an idea now, as I said earlier, that UberCloud and SimAir were partnering together with these big hyperscalers to really get them, so to speak, more load from all of these different engineers that are now using the specifically tuned Docker containers with this nicely prepared engineering packages, so that the engineers, at Siemens and whatever, can just nicely, using these, and then with this have less complexity in really using computing, and maybe don't even need to deal with virtualization, VMs, doing this because the container enables you more easier deployment of all of that, so that you as engineer can focus on your domain. Now, again, I think we're coming into more and more, let's say, repetition to really teach, let's say, this technology in depth. We would require maybe 3-4 lectures where we really pull then, out how Docker containers are created, recipes, and so on. But I think this is something rather for software development courses and software engineering courses, where containers have, of course, also now a big impact. Here, just now, again, how it really works in the cloud as examples. Again, OpenCarfi Cloud is something that maybe know some of you here in Iceland is one example. You see the different domains. Again, here's a car crash that we had already, but also the medical domain, for instance, can use some of these engineering packages. And then you very quickly at the point where this needs to be very simple for, let's say, health specialists or healthcare specialists, right? So here you see also impact of deep learning these days, and also the different cloud providers, right? We talk here about OpenCarfi, but also here using OpenForm on UberCloud and Microsoft Azure, for instance, what you already know. Now you can go on and you see again Microsoft Azure, for instance, for an ANSYS simulation for airbags. Basically, also very practical example where you would use that kind of technology to help with the computer-aided engineering. You have again the Advania HPC flow we already mentioned, right? So again, Iceland is here also in the game. And this is using again our computation fluid dynamic simulation we just introduced a little bit. We see Airflow again using ANSYS, and you see quite the flexibility, right? So Advania HPC flow again, Microsoft Azure again, and UberCloud enables this, of course, by having this containerized approach. You can very quickly use, for instance, the ANSYS one that you see here to put it, let's say, from one to another cloud provider, for instance, or basically the CFD packages you prepared for performing, for instance, the aerodynamics here can be also nicely then, used in a complete different cloud as well. Important is that the Docker container is consistent, and that it works nicely with your Kubernetes engine. And then you basically have the opportunity again to see lots of portability option, which we maybe can also use to cut down prices. If one cloud provider is maybe too expensive, you can also switch. And I think with this, you get the story about the applications, the portability aspects of the containers, also, of course, the simplification. And you see here also the sectors when you think about when they do the idea of HPC, so working maybe also in the cloud, you see here the revenue that you do per HPC here is in the 83 millions. And, basically the profit or cost savings per HPC point that is here in the example of manufacturing just, right, is 20 million. So this is something which also shows you that this is a market which is a niche market in a way, because engineering in clouds is very specific already. But you see also there are lots of revenues and return of investments, which of course is then giving, let's say, fertile ground also to all of these different applications, and also then for revenues for UberCloud and SimAir where they're interested in. Again, maybe also comparing these a bit when you think about pure HPC in contrast to the UberCloud and SimAir containers, again, with all the different packages you see here, NumD for molecular dynamics, and GROMACS, for instance, we didn't really talk about yet as well, but these are also very known packages, in addition to ANSYS OpenFOAM we already discussed, for instance. So then the idea is that you have with the containers, of course, so this kind of flexibility we were alluding to. So you can, with the cloud, you don't really, as an engineering company, have to buy basically the HPC machines, right? You need HPC, that's clear as engineer. So we talk about really car design, car crashes. There's no way around it. But the idea now, of course, of putting this into the cloud is, cutting costs a lot, because otherwise you have to do that on site to create your own data center. And with this, you have change, right? You know that, of course, a different generation of GPUs, for instance, we discussed, from NVIDIA through all the years with, maybe V100s, A100s, now H100s. So this is something where you have to keep track, because all the packages will be maybe getting better and need more computing. And with this, having then a huge HPC data center on site is maybe something which is for engineering companies and really hard, right? Of course, many of them have done this in the past, and many of them still do it today, right? So it's not that everybody is now pottering off directly to the cloud. Some of them maybe create an in-house cloud around it, something we will explore also in one of the next lectures when we talk about OpenStack, right? To create your own cloud. But this is really, let's say, the benefits of putting this now into containers instead of running, let's say, directly on the HPC without any container support. That means you install it via each of the individual HPC service centers or in your own center. And then you basically have to keep track of the maintenance. You have to update all these different containers, and do it yourself. But by using, of course, an UberCloud and SIMAIR solutions, all of that is done for you, right? So these containers are already, let's say, prepared, and all what you have to do is then to decide probably on which of the HPC clouds you want to jump on, right? You see an example of the Azure High Performance Enterprise Cloud Platform. We have also seen the HPC clusters in Amazon, right, which were at the end of one of the lectures there, which are then really the larger set of resources, going way beyond what we did in our examples at the beginning of the course, where we just picked, let's say, one EC2 element. So there we're talking really about HPC and larger needs. So in a way, then this gives you this fantastic term that we already had from the beginning in the course, this HPC as a service. Hence, the service approach again is, of course, key here, alluding to the fact that we really have in HPC a lot of complexity. So to be an expert on that level requires lots of different expertise in coding, in installing libraries, understanding underlying hardware technology. So interconnects, for instance, between different, let's say, nodes combined with different vendors of GPUs, for instance. So et cetera, et cetera. HPC is complex. Of course, it enables a lot. Hence, the idea of doing it as a service character to really, let's say, provide a platform, if you want, for engineering simulations, making it easy for the engineers to really have their typical, let's say, innovation process, which is, shown a little bit here from design over operation up to innovation, and then, iteratively improving the design. And HPC is somewhere in the middle, but it is nicely hidden in a way from EverCloud and UberCloud and SIMAIR containers. So this is, let's say, an enormous win for the productivity of an engineer who otherwise needs to, go to their own data center, install packages again, maintain maybe OpenFOAM, for example, over many years. And here you just basically pick the container that is already ready-made for OpenFOAM. It is serviced in this sense. It's also up to date in terms of patches from all sorts of, bugs perhaps. So this is something where HPC as a service is now an interesting term in the course that is, of course, alluding to the simplicity that comes alongside this. And then there's one element we didn't really discuss, which is then the licensing of these technologies. For instance, ANSYS and many of those here and there have also license aspects. So when you use it from the container, you also need to have a license sometimes, right? Not everything is open source, like OpenFOAM, for instance. So in this sense, there's a license approach as well that enables you then to, for instance, get to a license server and run also these license, let's say, usage applications. And this helps, of course, for instance, in computer-aided engineering a lot. And I want to basically finish, because we are almost over time now, to just some related topics that I would continue to teach if we would have more course hours together. But you know, the course is coming also to a close. I'd rather give you pointers into different directions. So that, of course, is one which is very important also for the HPC in Europe, because many of the HPC and Euro HPC sites you see are mostly offering the container support through Aptainer, or previously also known as Singularity. It has similar concepts as Docker. It's basically very similar and can even also handle Docker files. So you basically on a relatively safe side if you pull a Docker image. So in a sense, that is very good. But still, think about that HPC centers are still a little bit different. So not every center is offering it. That there's also a kind of a version against from Docker and Java. So basically, HPC is an area with C, C++, C#, and maybe Python are much more, and even Fortran used than Java. So also there are some, let's say, careful considerations when you come basically to your bosses in the company and say, I want to run, let's say, this Java application, HPC. They will look a little bit, you know, and into your eyes and think, what the heck, what do you want to do? But of course, with the container technology, you can circumvent this a little bit. And it's also not that I talk here against Java. Java is useful for many things. Just saying that these large infrastructure elements are usually not used to work a lot with Java. Then we have seen also in one of the slides Kubernetes as a nice orchestration element to really, you know, basically have a larger cluster. So a similar technology is Apache Mesos, in a way that it really abstracts them from other computing resources that are available. You can combine them on different, let's say, platforms even. I think one key element to understand is here you could, with this Mesos example, for instance, combine the world of HPC with an MPI application that is scheduling an MPI job maybe on a HPC machine with the concepts we discussed with MapReduce, Hadoop, and you would maybe combine this then in a large application, right? So hence, it's another orchestration element that you basically can use to really have a, let's say, more distributed system with many different ingredients created, like for instance, maybe also putting Apache Spark into the game, right? You have Hadoop, Spark, MPI jobs, and with this you do quite a lot in computing, especially if you need, you know, high-end computing, clouds, and HPC. Good, yeah. In a way, these would be topics to do next. So discussing Mesos maybe more in detail, and also then the related technologies, again, the Zookeeper and so on that you have already touched base on with Apache Spark, if you remember. But I think that's all what I want to talk about today. I still think that the IcePack here is good for you to look, a short video that you see a little bit, you know, how ANSYS now works and abstracts really from the underlying computing element. That is quite interesting. And the same way it can be used with UberCloud, you know, containers, of course. Some bibliography. And with this, I would say we see us next time with an invited lecture 13 by another PhD of mine, Marcel Ach, that will talk about with you about hyperparameter optimization. So see you then.